Hello, everyone. Thank you for attending Manoj Penmetcha's PhD dissertation defense presentation. You know me, but just to introduce myself, my name is Byung-Chul Min. I'm associate professor in CIT, and also I'm chairing Manoj PhD committee and also his major advisor. Today, it's my great honor and pleasure to introduce Manoj Penmetcha for his PhD dissertation defense presentation. Manoj entered my research lab and started working with me since 2016. In fact, it was 2012 when I first met Manoj. At the time, Manoj and we worked together as graduate students on educational robot under different academic advisors. And then Manoj received his master's degree, and after that, he worked for Deloitte to help implement Medicaid program. Then he returned to academia in 2016 to pursue his PhD. I was so happy and excited when I was contacted by him, asking me to be his advisor, because I had already worked with him before and knew that he would be a very good student. So Manoj and I have been working together for the past few years for his PhD. Based on his unique undergraduate and master's and industry experience in web programming, cloud computing, edge computing, and machine learning, Manoj has focused on cloud robotics for his PhD. Actually, this cloud robotics is very important field of researches, as robotics and robots are increasingly introduced in our lives. And robot tasks are becoming more and more diverse, but still manual robots suffered from limited computation resources. I've never seen anyone as experienced and knowledgeable as Manoj in this field. That's how much Manoj excelled in these researches. And today, we'll be able to hear more about his researches. Please join me welcoming Manoj.
Thank you so much, Dr. Min, for giving such a wonderful introduction about me. Yeah, so I would like to take this opportunity to thank all my committee members for the valuable feedback, support, and insights. To be frank, it was based on the idea that stemmed from their foundation led to this research. So I'm very thankful for everything they have done for me for the course of last 2 or 3 years to achieve and be where I am right now. So jumping to this presentation, so my presentation can be broadly classified two steps. Like the first is like what research we have done prior to my defense proposal, and the second, let me add. So the first is what research I have done prior to my defense proposal, and the later is what research I have done after my defense proposal. So today I will be very briefly talking on a very abstract level of these two topics, because I have already covered most of these topics during my defense proposal, but I will be mainly focusing on the work which I have done post my defense proposal and expanding more on the work and how I evaluated and all those things. So the main thing, the motivation behind this study started maybe in 2017. That's when I think Professor Eric Dietz has suggested one of my friends about an algae problem which was happening in the pond nearby. So one of my friend Arvinda started working on machine learning models for algae detection and removal. So once we were working on that model, we realized that these models are highly computationally intense, and we did not have a framework through which we can implement these models on the robotic systems. So we realized the importance of a communication framework that helps robots communicate with an external computing resources. By providing the robots the external computing resources, the robots with the minimum hardware can do more complicated applications and be more powerful than what they are. So that is the whole idea. That's how it started. And we started working on this various architectures and various cloud platform, various application offloading solutions to even further this area of research. So broadly, my area of research can be categorized into four steps. The first is where we propose an architecture through which the robots can connect to the cloud. The second is like we evaluate the proposed architecture with a full offloading solution. And for the third and fourth part of my research, we have worked on application offloading solutions. I mean, sometimes robots come with a decent computation capabilities. We just don't want to deploy all the applications onto the cloud. So we proposed a couple of dynamic offloading solutions, which helps the robots to decide when to offload the application to the cloud and when not to offload the application to the cloud. So that's mainly about this research. Even though these papers are not part of the thesis, my dissertation, they played a very crucial role for me to understand the importance of cloud robotics for robotics as such. So the main literature review is like how it all started is in 1994. That's when actually people were starting getting used to the internet. So Ken Goldberg was first to successfully connect his telepresence robot to the internet. So he was the first one who was trying to connect the robots to the internet. And in 1997, Inaba was the one who kind of realized the importance of providing the external computing resources to the robots. And in 2009, some of the researchers from Edinburgh University, even though they haven't used the cloud, they have used their local computing clusters to provide a computational resources to the robots. And in 2010, when cloud computing was kind of kicking in, James F. Kaufner, he's kind of also known as the father of cloud robotics, first coined the term called cloud robotics. And he explained the advantages of using cloud computing for the robotics. So here we'll talk about major limitations in the current literature. So we did very extensive literature review, and we did find a lot of limitations in the current research. To be frank, the area of cloud robotic is itself kind of an understudied field of research in robotics. I mean, a lot of research has been done in mobile offloading, but cloud robotics as such is being a little bit understudied. So it's a need of the hour to do a lot more research in cloud robotics. So the first thing, what we found out from the literature is that cloud robotics architecture there are a couple of architectures out there, but the current architectures don't support the usage of external open source libraries. And they also fail to address the heterogeneous robotic setup situation. To address these two issues, we proposed an architecture which mainly concentrates to address these two issues. And we evaluated this architecture with a full offloading solution. Later, some of the studies also have been proposed which do not account for the robot's local computing capabilities. I mean, here, if we see in the full offloading, whatever is the case, we just offload the application onto the cloud without taking the consideration into robots' local computing capabilities. So there is a lack of research in the area of dynamic offloading. So we want to maximize the usage of robots' local computing capabilities and minimize the dependence of cloud computing. We only want to use cloud computing when it's necessary, not all the time. To address these limitations, we have proposed a couple of novel state-of-the-art architectures in later part of the research that we'll be talking in third and fourth part of my research. I think this is an important thing for me to mention, a couple of performance evaluation metrics. So these are the very important performance evaluation metrics that one uses to evaluate the performance of an architecture. So for the latency, what it means is the amount of time the application takes for execution. And scalability is another important critical issue because robotics is mostly a synonym for multi-robots. So when there is a lot of scenarios where there is always multi-robots interacting with each other. So the architecture should support scalability of robots. I mean, they should support multi-robot scenario and the energy. Robots also come with limited computing capabilities. It's also important to design an architecture which reduces the energy usage of the robot. And third, interoperability. As you know, robots are equipped with variety of sensors which are manufactured by variety of manufacturers, and even robot work on different software platforms. So the interoperability is one of the most important critical issues that the architecture needs to address. In our research, we really wanted to consider all the performance metrics, but we mainly focused on two of these. We mainly focused on latency, and in our architecture, we also focused about interoperability issues. So in this presentation, I will be talking a lot about ROS and cloud computing. So I thought it's important that I clarify what it means, what ROS means, and what cloud computing means. So ROS is a de facto standard for writing robot software. It's a flexible framework for writing robot software that supports many of the industry hardware. So if you see in this figure, the ROS master is like a OS operating systems, and nodes are the different are the something which are assigned to the sensors, and they get the data and they publish the data in the form of topics between different nodes and send back to the OS for processing of the data. So ROS is an open source, modular, easy to use, and low level of control, and most of the people in robotics use ROS. And it also comes with a decent amount of robotic packages which can be readily used for the applications. The next important key term that we will be using throughout is called cloud computing. So with technology advances, the future is set to be highly competitive, and agility is the need of the hour. With cloud computing, the organizations can usually save a lot of money by using an external storage, servers, and management services. So cloud computing is an on-demand delivery of computing power, storage, applications, and other resources. Broadly, these cloud computing services are categorized into three types. They are infrastructure as a service, platform as a service, and software as a service. Let me give you a brief examples of each of these. The software as a service is something where the user has the complete software solution, where he will be just consuming the application solution without doing anything to the solution. Like example for that would be like a Dropbox, which we use. And the platform as solution is like we have a bits and pieces of the software, and we need to connect them all together to make it useful for us. For example, the example would be Google App Engine. And IaaS is like a bare minimum hardware where we need to start from the scratch, where we need to deploy our OS and everything and make this work. So that's a brief introduction about my presentation. The next important thing is like we will be talking about architecture and full offloading. This part of the research I have already discussed during my dissertation proposal to save time and focus on the other two parts which I have done the last 1.5 years. I will be very briefly talking about this topic in an abstract manner, but if you guys have any doubts, we can talk after the presentation. And we also have a paper published on this topic that can be, and the title for the paper is so and so. So what is an architecture and full offloading? So the cloud robotic architecture is a framework that facilitates robots to connect to the cloud infrastructure. Our architecture, as I said earlier, kind of designed to support heterogeneous robots. They also support robots with ROS and non-ROS systems. And we also, I think we are the first to do this. We provided the usage, we facilitated the usage of JavaScript packages to the robotic applications. I mean, we added a new dimension of packages to these robotic applications, and we kind of demonstrated how it works as well. So the overall architecture, what we designed is like this. So the architecture mainly consists of two layers. The ROS-based robots connect to a JavaScript server using a ROS bridge protocol. The ROS bridge, sorry. Yeah. The ROS-based robots connect to our cloud service using ROS Bridge, and how it happens is ROS Bridge is a communication. It's like a web communication framework provided by ROS, and JavaScript receives the information from these ROS robots and processes it accordingly. So if we need a package that from JavaScript library, we have a data conversion tool which converts the ROS messages to appropriate message types, and we can apply different JavaScript libraries on this, the input information we got from the robots. And for if the robot is looking for a ROS-based applications, we have a ROS instance running on the cloud, which provides the open source, all the available ROS packages that can be consumed by this robot. On the other side of the diagram, we see non-ROS based robots. These non-ROS based robots establish a communication to web JavaScript server, and the response they get is in the form of web services. So the web services provides the response in the form of an XML file, and they can subscribe to that XML file, and based on the results they get from our web services, they can act accordingly. So that's about the architecture, and we evaluated the architecture with a full offloading mechanism. So, I mean, with robots, as we see here in the picture, they come with a bare minimum computing capabilities. I mean, for them, for this kind of robots, if we want to run a computation intense application, cloud robotics is an obvious choice. So full offloading is an obvious choice. So these robots will be just sending out the sensor data, and at the end, the cloud computing will be processing those sensor information and giving back the results to these robots. So we evaluated the architecture in the terms of CPU utilization. So what we wanted to do here is, like, we used a ROS package called gmapping, and we ran the application both on the cloud and on the local machine. So what we observed is that when we don't use this architecture, gmapping was consuming more than 100% of the CPU. Here we are using 2-core CPU, so the CPU is 200%. We can see that gmapping was consistently consuming more than 100%. While if we use the architecture and we deployed the gmapping on the cloud, and the robot was just responsible for sending the ROS sensor information to the cloud, we can see that the CPU usage was less than 15%, and we can see a 10-fold decrease in the amount of CPU usage when compared with and without the cloud robotic architecture. For the non-ROS based robots, we used iRobot Roomba with Kinect connected to it. So this Kinect was streaming the image stream, and the web services was sending out the results in the form of an XML, which the robot can subscribe and act accordingly. To demonstrate all this scenario, we demonstrated a heterogeneous robotic setup. So the goal of this study was to demonstrate heterogeneous robotic setup, and the scenario was search and rescue operation. So the goal is the robot running with ROS will be publishing the global map of the area. In that area, this robot will be navigating and will be trying to find an object of interest. And we made a small video on how it's done. So here we show CPU utilization, how it varies. So this is with gmapping running on the robot, and we see that it's consuming substantial amount of GPU on the robot. So this is with the architecture, and we can see that the CPU remains stable always at 30%. So this is a heterogeneous experiment which I spoke in the last slide. So the first robot was navigating, and it was making the global map of the environment. The robot behind it was navigating in the global map the first robot has generated, and it's trying to find an object of interest in the global map. So they were working in a collaborative fashion. And they are also a heterogeneous robot setup because the first robot was running on the ROS, while the second robot was not running on the ROS. So that's about the first part of the research. I have spoken very briefly and on an abstract level. So for the last 1.5 years, my major focus, since my dissertation proposal was on the dynamic application offloading algorithm. So I've been working on various application algorithms which makes robots smarter. I mean, so if the robots these days come with computationally capable, I mean, their hardware is decent enough. I mean, if there is an application which can be successfully deployed on the robot without the requirement of a cloud computing, we just don't want to completely offload the application to the cloud. So here we designed the algorithm which takes into account of various cost parameters like latency and decides based on the latency if the application should be deployed onto the cloud or the application should be executed on top of the robot. So on a whole, we do not want to underutilize the robot's own computing capabilities. So the first thing we'll be talking about here is like a deep reinforcement learning based offloading based algorithm. We submitted a paper on this to IEEE Access, which is currently under review. So the problem, I mean, the why we needed to use deep reinforcement learning is what I try to establish over here. So the offloading problem is non-convex. What I mean by non-convex is like there are multiple applications and there are multiple robots. To be frank, reaching a global minima for all these robots and all the applications is an impossible task. If we had one robot or one application, maybe we could reach a global minima and we could use that algorithm. But as we deal with multiple number of applications and robots, the general machine learning algorithms don't generalize well to this. And it also, as the number of applications increase, it also becomes an NP hard problem. So to address some of this issue, we use deep reinforcement learning based techniques. So deep reinforcement learning based techniques is some of the, they are relatively new to the machine learning algorithms, which have been proposed in last 5 years, and they are extensively used in robotic applications. So at first, we will not be using conventional algorithm because they do not again scale well to the increasing number of applications and robots. As the state space increases with number of applications and robots, there will be an explosion in state space, and ultimately our reinforcement learning agent will not be ever learn anything constructively because of a lot of space values. Instead of solving the problem using a conventional optimization method, we proposed a reinforcement learning based solution that is called based on DQN. So we formulated the application offloading problem as a Markovian decision process. So the Markovian decision process is nothing but it consists of 4 important characters. So they are state space, action space, reward, and transition probabilities. And we used deep reinforcement learning based DeepQN approach to solve this problem. So DeepQN is an off policy and a model-free reinforcement learning based algorithm. DQN also works on the principle of selecting those actions that maximizes the overall reward in the long term. So this statement will be better explained in the next slide. So these are the major equations for the DQN. So the DQN works on the foundation by the Q function. So Q function is nothing but what it says is that it gives a reward for the current state action pair represented like this, and the maximum reward value expected in the future, where this lambda is the discount factor. So the Q function is the current reward plus the maximum reward that it can attain in the future. So by using the Bellman equation, we can further simplify this value as following. But what we do, this is like a traditional queue learning method. So we use deep QR network. So what deep QR network does is like it introduces a neural network to this new this queue function, and it tries to learn these values. I mean, it tries to have a loss function defined like this, and it tries to have a global minima based on the values it gets from these equations. As I said earlier, we have formulated the application based as a Markovian decision process. So the Markovian decision process, the most important thing is how we define our state space, action space, and reward. So we define our state space using these three variables. For the first variable is the data size, the second is CPU availability, and third is the network latency. I want to point out to one of the most important assumption or these we made in this thing. So this is not an assumption, this is actually technically proved as well. So we say that time of execution of an application is proportional to the size of the input data. So that's how as we design our state space. So D represents the input data size of an application. In the next, we have an action space. Our action space is simple. It's a binary action space, either to offload or not to offload. And the reward. So this is again for the model and the agent to learn a good policy. The reward plays a very crucial role. So how we define our reward is as following. For the onboard computation, we calculate the times. We calculate the local execution time by subtracting the timestamp at the application completion minus the timestamp at when the application has started. So this way we can get the application execution time for the local computing. Similarly, we also do the same for the cloud computing as well. Here we also introduce two tuning parameters, alpha and beta. So the reason we introduce this tuning parameters alpha and beta is that we want to give the robot operator an option to prioritize a choice between offloading and local computation. If the robot operator believes that doing the execution onboard the local computation is a higher priority, he can set alpha value more than beta value. But in our experiment, we did not assume any predefined priorities, so we always set alpha equal to beta. So for the complete total computational cost, how we calculated that we multiplied the tuning parameter with the local execution time, we get the total computational cost for the local machine. Similarly, we also get the cloud for the cloud by tuning parameter multiplied by the application execution time for the cloud. And here at the initial stage, our algorithm takes a random action between, when it's trying to learn, it takes a random action between the local and the cloud machine. So we define our reward function as follows, and we normalize it by adding the total computational cost, and the value will be always in the range of -1 to 1, and this is a variable reward, it's not a constant reward. This kind of helps the robot to form a consensus much quicker than having a constant reward. For the simulation part of it, this was the most important part of it. Proposing algorithm was one part, and validating the algorithm, I think, is the most critical and most challenging part for any experiment. So what we have done was we have used a simulation environment. This is based on ROS Gazebo, the simulation environment. So we have used as kind of a city environment. We have placed a small husky over here. So the husky needs to find path for various destinations in this map. So that is the task which the husky needs to do. The global map for the robot for the graphical environment which we saw in earlier slide is this one. So these are the obstacles. This is our husky, and for example, in this scenario, it had a destination set to this point, and this was the shortest path for the husky from this goal position to the ending position. And this is the camera view of the husky. So our navigation application framework can be broadly categorized into two types. For the first, on the top, we use a ROS layer. The main purpose of this ROS layer is to obtain state space values. On the bottom, we have a DQ and training layer. So whatever values we get from the ROS layer will be stored in ROS bag file and trained on a DQN network for optimal decision making. Again, the most important thing in our presentation, as I said earlier, was that we make an assumption that application execution time is based on the application input data size. So it's important for us to properly represent the input data size for a given application. So how we did that was so in this example, we see the robot was at starting position A and it needs to go to a goal position B. And the navigation path which our algorithm suggested was this orange line. So here we use Dijkstra's algorithm to find the shortest path between A to B. So here we need to find what our ultimate goal is, that how many nodes our algorithm needs to explore before finding the shortest path between A to B. So that we want to find that and use that as an input data size. The best way to do that is that we believe can be done by finding an Euclidean distance between A to B and having a square or rectangle on with an Euclidean distance x, and finding the number of nodes in this rectangle area gives us a good estimate on the number of nodes our algorithm traverses to find the shortest path between A to B. So as I said earlier, the Euclidean distance between A to B is given by x. The area of the rectangle with AB as a diagonal is half into x squared, and the number of nodes, area of each node can be represented as r squared. For ROS, we usually by default it sets the area of each node to be 0.00525, and we divide the area each node by the area of rectangle to determine the number of nodes inside this rectangle. So this way we can find the number of nodes inside this rectangle. So here we see that how we calculated. So this was starting position and this was the goal position. The Euclidean distance between A to B is 45.29. The number of nodes between A and B was like 410,000, and the number of nodes it needs to travel to find the shortest path is around 5 million. For the communication of it, we used Amazon Web Service as a backend provider for the cloud services. We used instance based on Ohio, Amazon to do this. And as a communication protocol, we use 0MQ communication protocol. So 0MQ is a high performance asynchronous messaging library, and it's one of the very well-known communication protocol out there. And the latency, what we observed was 30 milliseconds with a variation of 5% for the 99% of the case. So it was a pretty stable network latency. So the local robot sends out the LiDAR data, the current position, and the goal position. The instance a ROS instance running on the cloud processes these three data and sends back the planned path to the robot. So the overall DQN network, and we have represented like this. So we have, as you see, we have a gazebo environment which is connected to AWS. We have state space, we have action space and reward. But what we want to focus on this slide is that the neural network we have used for this training. So I mean, we have used like one input, 3 hidden layers and 1 dense input layer. To be frank, we have not experimented much on this. If we change this parameter, it might have performed better or not. And again, this can be changed, but for our experiment, these settings performed decently well. So we stick with this neural network settings. So coming to the results and analysis, I mean, if we consider traditional machine learning models, model evaluation is kind of straightforward because we kind of have a validation set and we kind of use the validation set to see how well our algorithm performed. But coming to the deep reinforcement learning, it's kind of tricky to evaluate how the model performed because we don't get much information about the accuracy and all those things. So to evaluate our proposed algorithm, we used two kind of techniques. One, we used a real data set, the real experiment, and we also synthesized the data set, use a couple of synthetic data set to see how the algorithm performs. For synthetic data sets, we know how the algorithm should perform. So we were evaluating if the algorithm is performing as it's supposed to perform. For the hardware configuration of the experiment, this was the hardware configuration. Our local robot was configured like this. I mean, to be frank, it was decently powerful robot. And our Amazon AWS, we used a AWS X2 large cloud instance for this experiment. So I will show you a brief video about our simulation, how it works. Here we initialize our gazebo world. In the next, we launch the Husky robot. So this was a Husky robot which has been launched. And the third, we run a node to find the CPU availability at a given instance or a given state value. And we publish all this value using a state space node. And we establish a communication protocol with cloud using a ZMQ. And we record all this information using Raspberry records. So for the simulation part, to ensure faster simulation, we did not actually move the robot. Rather, we were just calculating the shortest path for various destinations by making Husky static at a given position. So we can see we are trying to calculate different paths for different locations in the map, and we see the local execution time, cloud execution time, and this was the starting position, goal position, and the number of nodes or algorithm needed to explore to find the shortest path. So we did this for more than 10,000 simulations for both to get the data set. So that was the experiment what we did. So the first thing is that we want to evaluate on the real data set, what actually, how it performs. So the first thing which we saw was the loss function and the cumulative reward function. From the loss function, we are able to see that our agent was learning a policy that teaches it what it needs to do to get a maximum reward. So maybe we can say around 300 time step, it kind of form a consensus about, what actions it needs to perform to get the best possible reward. So we can see that the reward values are also kind of increasing as the sequence progressing. It implies that our agent has learned a policy to get the best possible reward. So, but seeing the loss function and reward function, we do not kind of know what policy our agent learned. So what we did was we plotted planning size, input data size against the time step and what action our algorithm has taken. So the blue dots represents that our algorithm has taken a cloud execution option, and the red dots represent our algorithm has chosen the local execution option. So we represent a threshold over here with 1.1. So what we can say that our agent has learned a policy that if the input data size is greater than 1.1, the best possible action for it to use cloud computation. And if the input data size is less than 1.1, the best possible action would be to choose local execution. This also validates our proposed assumption that data input size impacts the application execution time. So this way we can say that having the state space value with application input size would be a good estimate for figuring out the application execution time and making offloading decisions. Similarly, the next thing what we did, we we understood the policy and all those things for the real data set, but we want to explore it even further. So we synthesized the data set, we generated very synthetic data sets, and we know how the algorithm should perform, and we saw the loss function and the cumulative reward functions to see if the algorithm performed as it's supposed to do. Here we see that what we did was we got the application execution time for the local computation, and we have multiplied the application execution time with 0.9 to above 1. So that way we always made sure that our cloud execution time was always higher than the local execution time. And we trained our algorithm based on those data values, and we see that the reward value is decreasing, and at some point it understands that the best possible scenario for it is to get no more negative rewards, rather stabilize and take reward zero for any given instance of time. Similarly, we also plotted the dataset for cloud only dataset. So here our dataset had application execution time for the cloud always greater than the application execution time for the local. And we can see that, I mean, the loss function decreasing and it's kind of stabilizing at 0.03. It kind of says the convergence, and even the reward values kind of increasing for every time step. That implies that, you know, our algorithm learned a policy that by always choosing cloud computing, it gets the best maximum possible reward. And similarly, the third synthetic data set, what we validated was for CPU based. So we had a CPU threshold value. So if the CPU threshold value was less than certain amount, we set the local cloud value to be less than local values. Similarly, we set the cloud values greater than local values when CPU threshold was greater than the defined threshold. Again, as observed, the convergence reached at convergence, and our reward also gaining for every time step. We plotted those values against as a choice analysis part. So we have plotted the action taken and the CPU available value. So here we set the predefined value of CPU to be 0.6, and we plotted against it, and our algorithm has learned accurately, and this was some of the wrong actions. I mean, this was usually happened in the initial phase of training, and our accuracy was also greater than 94%. And finally, we evaluated the proposed algorithm with long short-term memory. So what we did here was like we implemented LSTM and we tried to predict the application execution time for both local and cloud execution. Based on the application execution times, predicted execution times, we have chosen the predicted actions, and we have compared the LSTM predicted actions against our proposed DRL algorithms. And what we can see in this experiment is that our DRL algorithm kind of always outperformed the LSTM algorithm by at least 9 percentage points better than the LSTM algorithm. And finally, I would like to discuss some of the limitations of what we have in the presentation which we did. So we say that our state space is built on the input data size, and to be frank, there is no true guideline that defines how to correctly represent the size of an input data size. For example, a path planning input data size can be n log n. If you want to randomly search n elements, the input data size is n. The binary search is log n. So it's very varied, and there is no ground rule which defines how we need to define the state space. If we don't define the state space properly, there's a very good chance that our algorithm might not learn a policy for effective offloading. So offloading of the application. The second limitation of the study, what we have done was we have carried out the experiment in a perfect simulation experiment setting. For example, we have carried out the experiment in our local computer, it always had a stable internet connection through LAN connected to the AWS. So the network latency was always around 30 milliseconds. But to be frank, if we go onto the field, this might not be the case. There might be network drops and all those things. And we did not get a chance to consider that part of uncertainty in the experiment. So to conclude this part of the presentation, so we have proposed a dynamic computational offloading solution based on DQN, and the state space is built on the assumption that the data size of an application directly impacts the execution time. And we also observed that the overall accuracy the training was always greater than 80%, and the results also demonstrated that the agent was always able to learn an appropriate policy about when to offload the application and when not to offload the application. So that was the second part of the presentation. The third part of the presentation, we have the last part of our presentation, we have proposed a predictive modeling algorithm. So the motivation behind for us to propose this predictive model is that sometimes we don't want complex machine learning models to train for a long time and make predictions based on it. We want to have a lightweight models which make decisions on the fly after the application is initiated. So for it to happen, it needs to learn about the application and when to offload as quickly as possible. So that was the whole motivation behind our predictive model algorithm. So our generic architecture is like this. So we introduce a generalized predictive for application offloading. So we categorize application A into different subtasks of AI. And our basic premise is that we can predict application execution times, and based on the predicted application times, we can take appropriate actions. And the biggest underlying basis of the proposed algorithm is that we train it on only the fixed size of previous n values. So the robot sends out the input data, and our predictive algorithm learns on the previous n values, and based on predicted action, it chooses between the ROS package or the cloud execution. After executing the application on the predictive algorithm chosen hardware, we store back the value again to the queue, and this queue again will be refitted on the predictive algorithm for the next prediction. So we have used a simple linear regression based model with least square methods to predict the execution times for local and cloud computing. So what we have done was we have used the application input data size along with the time of execution of the application and use the least square method to define the slope, and we calculated the intercept, and using this way we were able to calculate the local prediction time. Similarly, we also calculated the prediction time for the cloud computing as well. And we have used the following navigation framework to evaluate our experiment. So what we have done was we have used again a gazebo simulation environment where it was connected to AWS. The data from our robot is stored in a queue of size n, and we feed our linear regression model with all these values, and a predicted action takes action based on the application data input size. So we get a data input size, and the predicted output would be a couple of execution times of both of them, and we send out, and the gazebo environment then rather does experiment evaluation on the robot or on the cloud. So the major thing, what we want to evaluate here is that we claim that we want to train on a fixed small data set size of n of the previous n values. So it's important that we understand how the algorithm performs for various n size values, various data set values, like for 5, 10, 20, and 50. So these are the various data set sample sizes which we have used for algorithm training and evaluation. And we have evaluated in terms of correlation, residuals, accuracy, and again we compared with LSTM. This is the algorithm which we have used. So we initiate to data first in first out queues, and we store all the values, and we append the values from A, B, and fit the values to a linear regression model, and we try calculating the application execution times. So I would like to again show a brief video about our simulation environment, again what we have used. This was simulation environment similar to what we have done. So again, we have launched Husky robot, and we initialized ROS, and we have a cloud communication with ZMQ. And again, we have used a Dijkstra's algorithm to compute the shortest path to get the data sets input. This is very similar to what we have seen earlier. So as I said, we would like to evaluate our proposed algorithm with respect to correlation, residuals, and accuracy. The first thing we do is we evaluate the proposed algorithm with respect to correlation. So we take various n sizes, like n equal to 5 to 1000, and we evaluate how the correlation varies. Here we can see that when the n is small, the correlation was actually higher, which was to our surprise. I mean, to be frank, as the data size increases, the correlation should also increase, but we were surprised to see that as the n size was increasing, the correlation coefficients were also increasing. Here we used Pearson correlation to find the correlation between our data size and the application execution time. One thing we observed is that for the cloud, we had a low positive correlation, but whereas for the local machine, we had a higher positive correlation. That kind of validates our point, when for the cloud computing, it always has a limited onboard computing capability. So as the application data size increases, there is always a strong increase in the application execution time. But whereas our cloud is computationally powerful, even with the increase in application data size, there will not be much increase in the application execution times because the powerful nature of the cloud computing. So there is a smaller correlation between them. And other thing which we want to point out is that this correlation kind of justifies one of the assumptions which we made in the research, that we having a small data set sizes of previous n dataset values, we are able to capture some of the exogenous factors that influence the application execution times. So for example, there can be several exogenous factors at a given instance of time. There might be multiple number of applications which are running, which kind of affect the application execution times. But these are all periodical in nature. They are not stay throughout the execution time. So having a small data set of previous n values, we were able to validate our assumption that exogenous factors are captured, and we are able to accurately make predictions using a small data set values. And we plotted the residual values as well. So for the residual values, we plotted our actual execution time with our predicted execution times. And what we see that is when the data set was small, there was a very high error rate, but as we are increasing the number of sample size, previous and sample sizes, the accuracy was getting better and better. But overall, what the biggest takeaway from this is that for the cloud computing, around 40, the accuracy started getting very good. For the local computation, around 20 itself, the accuracy is starting pretty good. Overall, we considered if we have a data set of 40 or so, the accuracy was more than 85% for predicted actions. So we plotted our accuracy in the graph. So we plotted our accuracy for various n values, and we also plotted the green line is the overall accuracy for the entire data set. We used the 80-20 training and validation split, And we also used a linear regression model with the entire data set with the 80-20 training validation split. So this starts from 50. This curve may sound very steep, but look very steep, but that's not the case. As you can see, by around 40, we already acquired an accuracy of 80, more than 78%. But the maximum accuracy we could achieve by using the entire data set would be around 82%. So if we are content with the accuracy of little bit lower accuracy, using the just small sample size of n of previous values would be good enough to make accurate predictions. So to discuss about what we have proposed in the this part of the presentation, we have, as I said earlier, there are several exogenous factors that can directly or indirectly affect the application execution of the applications. So, it's not always possible to capture all this and train a machine learning algorithm. So we kind of capture a very fixed set of previous n values with the minimum information and train the regression model to see if it can make accurate predictions. And finally, the drawbacks is that very particular to the thing which we have done was that linear algorithm is, as we are using a very small data set, it might be usually sensitive to outliers. So we have to write a logic to address this. Outliers will not be considered for our training purposes. And we also need to have some kind of linearity between the data. And to conclude, we had we can say that we had an acceptable error in prediction accuracy when n values were greater than 40. So to conclude my research, which I have done during the past of my 3 to 4 years, is that in the first part of my research, we have worked on developing a cloud robotic architecture, but we want to make it a state-of-the-art robotic architecture. So how we did was like we added access to open source JavaScript libraries, and we also added a functionality where it can handle heterogeneous multi-robot platforms. And we implemented a RESTful web service to communicate with non-ROS based robots. Actually, we believe still now there are no other studies which deals with these 3 things what we have done. And finally, we have evaluated our proposed architecture with a full offloading in terms of CPU usage. And the next thing what we have proposed is a dynamic application offloading algorithm based on DQN. And we defined a state space based on the input data size. And we also defined our reward function, the variable reward function. And we demonstrated in our results that it was able to train faster and converge faster. And to better analyze the data, we kind of analyzed the data set on real data set and a synthetic data set. And again, to be frank, this is one of the novel and state-of-the-art algorithm which has been proposed for cloud robotics for application offloading. And for the predictive algorithm, our other motivation was to make a lightweight offloading algorithm where the algorithm can start learning after the application has initiated and without any predefined knowledge about the application. And so we used linear regression for validation, and we used various fixed data set of n of previous observation to train it, and we experiment with previous n observations for accuracy and error. So the future direction is, this is something which I would like to spend some time. This is one of the, I believe cloud robotics is one of the most understudied area of research in robotics. There is a lot of scope for research in this area. So the first thing is that in our research, we were just considering latency. We could, for this to start off with, we could add on other cost parameters as well, such as energy and other cost parameters, which could make it more complicated. And we could also accommodate a multi-robot scenario as well. So the proposed algorithm, we just validated with a single robot, but we can just say that maybe we'll add a distributed system and make it work for multi-robot, but that's not research. So if we really want to add a multi-robot scenario, there are certain novel algorithms like DDPG, everything, which can take a single state space values and have multiple actions for a single state space. So this way we could address a multi-robot and a multi-application scenarios much more efficiently. And we did try to run a multi-robot algorithm on our application as well. And the other thing which we could do is like to have a prioritize some of the mission critical applications. So for example, for any given instance of time, we'll be having multiple applications running. So we can have a prioritization mechanism which defines this application is of high priority, so the latency should be of high priority. So the other application, whereas is of not of a high priority. So further application specific application, saving the energy of on the robot is of high priority. So we can have this complicated setup of prioritizing different applications and having a different algorithms for different kind of applications. And at the final thing, we use the linear relationship for like make prediction in the last part of the research, but we can also use some of the just a time series analysis algorithms without any linear relationships, such as ARIMA and SARIMA for predictive offloading. So these are some of the publications that I have done during my course of my PhD. And finally, I would like to acknowledge all my committee members for taking the time and efforts and guiding me through this research. And I said earlier, one of the paper which we have worked as a team was the whole foundation for this research. And also, I would like to thank all the Smart Lab members. Without them, my last 4 years wouldn't have been fun at all. So the next thing is like, what I'll be doing after my graduation. So post my graduation, I will be moving back to India for good. So I will be taking up full-time responsibilities at NCC and Multiscale Technologies. I'm fortunate enough to come from a family where it has been set up by a family. So NCC is like top 5 infrastructure companies in India. So I will be joining the company and helping out our parents to day-to-day activities. And we also had a startup which was set up last year called Multiscale. So we did set up in 2019. So it was set up with under the supervision of Professor Surya Kaldindi. He's a family friend as well. So what we do here is that we work on software solutions for accelerated material development. And last year we also got a seed funding from one of the largest semiconductor industry in US. And we closed a couple of high value contracts, and I've been remotely managing all these things. We already have a team of 15-16 software developers back in India, which I'm remotely managing. So I want to go back and I take up a full-time responsibility on running the company. So that's about me. Any questions I would take right now?
Okay, great.
Thank you,
Manoj, for your wonderful presentation. And I'd like to open up the floor for the questions. First, I'd like to receive a question from the public other than committee members. So if you have questions, please unmute and speak up your questions to Manoj. Okay, it seems like no questions. But once again, I'll do. Okay.
I see that Junhan has a question.
Junhan, raise your question. The hands. Okay, Junhan, please unmute and pick up your question to Manoj.
First of all, sorry for the late, Manoj, but even though I couldn't see your old slide, but I know your research, so I just want to ask you a simple question. So as I know, you work on a cloud robotics. So where do you see the future in this area? Like, do you think like, for example, in my case, I'm mostly my research mostly lie on the hardware side. So do you think it's possible to implement like cloud robotics, like to the like a real world, like robots out there? So I just want to hear your opinion about the future of your research.
Yeah, so that's a good question, Janan. To be frank, cloud robotics is always, I think in 2016, people were reluctant to use cloud computing for their applications. If you see right now, most of the people, like right from our even OneDrive and everything, we are completely dependent on the cloud for storing the files, data, and everything. The same thing has also started for the robotics as well. People realize that whatever configuration they have for the robotics, at some point of time, it will be not sufficient to run the complicated applications. So they always need to have a computational capabilities support from outside where it can enhance the kind of applications a robot can run. So I think the cloud computing is the future, and most of the robotic applications and the robotic hardware will be in the next 5 to 6 years will be completely towards the cloud computing.
Thank you, Manoj.
You're welcome, Junhan.
Okay, thank you for question, Junhan. Any other question from audience? Okay, I hear none. Then I'd like to thank all of our audiences for attending this presentation. Thank you so much. And then the committees, we'd like to have closer meeting with Manoj. And once again, thank you for all attendees. We really appreciate it. And thank you and have a good day.
Thank you. Thank you, everyone, for taking time and attending the presentation.